Hello and welcome. In this video, we are going to go through solutions for the test one review. At any point, if you need to skip forward to a specific question, the timestamps will be in the description of this video. Okay, starting with question one, they're showing us different relations, both in table form and in graphs, and they're asking us, do these relations represent functions? So in part A, we're given a list of values for the domain and the range. And what we can notice right away is that the values in the domain repeat, and that we have a -7 and another -7 down the list as well. And so what we expect if this relation is a function, that anytime we plug in a value like -7, we should always get a unique value out. So in the first case, we get 1 as our output. But the next time we plug in -7, we don't get 1, we get -7. So this is enough to declare that this is not a function. So the relationship in part A is not a function. Moving on to the relation in part B, this table doesn't have repeated values for the domain. And thus, we can only assume, given this information, that this relation is a function. It doesn't fail the test that we just gave for part A. So we'll declare this to be a function. All right, so now moving on to part C and part D, we have some graphs, some visual representations of relations. And so we can apply the vertical line test to these guys to check to see if they are indeed functions. So anywhere I draw a line on these relations, a vertical line that is, I shouldn't have the vertical line intersect the graph more than once. So I could draw this vertical line anywhere in the graph for part C, and we'll observe it only intersects once. So thus, this passes the vertical line test. So the relation in part C is a function. Moving on to the last problem in question one, we can again apply the vertical line test, and we don't really need to go too far. Once we just draw one vertical line, we see this fails the vertical line test because it intersects twice. So thus, via the vertical line test, we observe this is not a function. All right, so moving on to question two. They're asking us to answer questions using the graphs of each following function or each function below. In part A, they give us a graph of a function, and they're asking us to state the domain and range to begin. So let's start with the domain here. So we're looking at all of the x values plugged into this function. And we can observe that the lowest x value is -3, right? We can see that on the x-axis here. And it does include a solid dot on this end. So we will indeed use a square bracket for the left endpoint. Next, we'll look to see what the highest x value is, or the greatest x value. And we see that to be +2. However, instead of a solid dot, we have a circle here. So this indicates to us that the bracket being used for the right endpoint should be a rounded bracket. So it goes from -3 to +2, and we'll put that rounded bracket here. Okay, so next, the range. Now we're looking at the y values. And so we note the lowest y value is going to be -4, and it is a solid dot. So we know that -4 is going to be included, and we use that squared bracket to indicate that -4 is included in the range. Next, the highest y value or the largest y value for the range is going to be +5. And here we're also including +5. Okay, so next they're asking us to find, I would read this as f of -3, or plugging in -3 into the function. So what we'll want to do here is to go ahead and look at the function given in this graph and see what the output is when we plug in -3. So here I'm going to x equaling -3. And then I want to see, well, what is the output value? So on the graph, what is the y value? So we'll observe here that f of -3, if I plug in -3 into this function, my output is indicated down here. So we see that f of -3 is equal to +4. Okay, the last question for part A, they're asking us to solve what is the x value that we need to put into this function to get the output to be +4. So we kind of do the reverse of what we just did. We look and we see, when is the output equal to 4? So when is, this function equal to +4? We see this happens in two different places on our function. Right here, we can assume, and right here as well. So the x values that correspond to this looks like it's going to be -1 and +1. So for this one, if they were asking us to solve what is f of x equaling 4, what are those x values? X would be equal to -1 and +1. Perfect. Okay, moving on to the function represented in part B. They again are asking us to state the domain and range. So in a very similar fashion to what we just did, we'll go ahead and start with the domain, thinking about all of the x values that are appropriate to plug into this function. And so let's go ahead and think about what's going on the left side of this function. We see this kind of arrow tip to this function. And so what this indicates to us is that as we go off to, you know, we would say -infinity, right, in this orientation, that all of the x values are appropriate and that the domain starts with -infinity. And whenever we have -infinity or +infinity in our interval notation, we want to make sure that we always use rounded brackets, because we can never actually equal infinity or -infinity. Okay, next, looking at the right side of our domain, we look at what is the highest x value possible. And it looks like we're going to be approaching +4. And we note we have a non-filled in point here. And so this indicates to us that 4 is the largest value as we approach it, but we don't actually equal 4. So we have a rounded bracket to close off our domain. Okay, next, moving on to our range. Our range starts very similar to our domain in that we had that arrow on the left-hand side of our function. And so this to us will indicate that the range will go all the way off towards -infinity on the left-hand side. And then the highest or largest y value as our output, well, we need to look at the y values and we see, well, that looks like to me is +3. And so 3 would be the right endpoint of our interval for the range. And we also are going to include that 3 into our interval for the range. Perfect. Okay, so moving on to the next part in part B, they're asking us to find what g of 3 is. And so here, what we want to do is go to the x value of 3. So I have that here, right? And look to see, well, what is the output here? That's what g of 3 is asking us. When you plug in 3 into this function, what is the output? And we see that looks like it's going to be positive 1. Okay, so next, the final part of this question is asking us to solve this g of x equaling 3. Here they're asking us, well, kind of the reverse of what we just did. What are the x values that you need to plug in to this function in order for you to get as an output positive 3? And so in this graph, the only time that we are equal positive 3 is at that very specific point, right? And we ask, well, what is the x value there? Looks to me that the x value is going to be equal 0. Great. Okay, let's move on to question 3. All right, so question 3 asks us to create a table of values, graph the functions, and state their domain. So it looks like it's a multiple part question, and they're kind enough to give us x values to plug into this function. And so we'll just start there. Let's start by just filling in the remainder of these table of values. And so I don't have too much space here, but I'm going to work off to the side of our table to kind of show what we would do here. And so our function is described as, this would be read as the absolute value of x plus 3. And so what we want to do here is plug in -5 for our first entry, wherever there's an x. And so it looks like there's an x inside that absolute value. And so we're asking, well, what is the absolute value of -5 plus 3? So what we'll do is start by just combining -5 plus 3. And so we would get -2 as a result, and the absolute value of -2, that's just going to be positive 2. Okay, so moving on to x equaling -4, we repeat that same process. We just plug in -4 wherever there's an x in our function. And we combine -4 and 3 to begin. And we would get, it looks like -1, or the absolute value of -1, I should say. And the absolute value of -1 is positive 1. Okay, moving on to -3. We plug in -3 wherever the x is inside our function. And we combine -3 plus 3. So if I had -3 and I added 3, the result would be 0. So the absolute value of 0 is actually just 0 itself. And now let's go ahead and plug in the last value, -2, wherever there's an x inside our function. So we'll have -2 plus 3, the absolute value of that. -2 plus 3, we get positive 1. So the absolute value of positive 1 is just equal 1. Great. Okay, so we started and we finished creating the table of values. Next, let's go ahead and attempt to graph these points. Let me go ahead and look at the first point here. And I think actually in this scenario, I'll just indicate that every tick mark or every crosshatch on this graph is equal to 1 unit. Yeah, I think actually maybe I'll go ahead and say every 2 is equal to 1 unit. So let's see, does that work? I've got, let's call this -1, -2, -3, -4, and ooh, just barely, -5. So it looks like we're good there and choosing that as our scale. So our first x value is -5. So I'm all the way to the left here, and then I want to go up to +2. So that's going to be right here. And actually, let me go ahead and change that color so it stands out for us. Okay, so the next point I'm going to plot is x equaling -4, and the output in that scenario is +1. So that would be -4, comma 1 right there. Right. The next point is -3, comma 0. So we see that to live here on the x-axis at -3. Moving on to our last point, we have -2, comma 1. So when I plug in -2, the output is +1. And let's go ahead and see here. Let's attempt, I'll try my best to draw a straight line, right? So between these points. So connecting all of these points. And try to extend that line off as far as we can tell. And so you might be familiar that this is the typical shape of an absolute value function. So we are on the right track here, and we can actually add arrows because we know absolute value functions go off in the appropriate directions as indicated. They go off forever, that is, sorry. Okay, so now we've graphed our function. Next, we're going to go ahead and move on to stating the domain of this function and the range. So the domain, we're considering all of the potential x values. And so we note, as we just stated, that the arrows can be added to the end of our absolute value function. And thus we see the left-hand side, this guy will go off to -infinity on the left. And it looks like the x values, we have an arrow here as well. That also goes off to infinity, but this time +infinity as we move to the right. And the brackets being used here, of course, are going to be rounded brackets. Okay, so finally, let's move on to the range here. The range is going to be somewhat similar to the domain. However, let's start by thinking about the lowest y value possible for this function. Note that we're not going off to -infinity, right? We're not going down really any further than 0, right? That's the lowest y value. And we can actually equal 0, right? That happened when we plugged in -3. And so I can use a square bracket on the left-hand side. But notice those arrows that we drew in on our graph indicate that as we move off either direction, right, as the x values go off to -infinity or the x values go off to +infinity, those y values are going to go off to +infinity. Perfect. All right, so that would be question part A of question 3. Next, we are asked the same thing for a new function. So let's start by just plugging in these values to complete our table. So here, let's go ahead and plug in -1 into our function to begin. And so we plug in -1 wherever there's an x in our function. So we'd be plugging in -1 underneath the square root. And so this might feel a little weird. And that's because, well, if we were just plugging in -1, our calculator would tell us, well, this is undefined, right? We can't take the square root of a negative number. So thus, this will be undefined or does not exist. We're trying to fit undefined here, right? Because we can't take the square root of a negative. Okay, so moving on to when x is equal to 0, we'll take the square root of 0, and then we're going to subtract 2 from whatever the square root of 0 is. So the square root of 0, and you can check this on your calculator if you don't already know, the square root of 0 is equal 0. And so we would have 0 minus 2, which as a result will be negative 2. Okay, so moving on to the square root of 1. I'm plugging in 1 wherever there's an x, and then I'll subtract 2 for whatever the square root of 1 is. So the square root of 1 is equal 1, right? So I'll have 1 minus 2, and 1 minus 2 is equal negative 1. All right, perfect. Okay, let's move on to the last entry in our table here. We're going to plug in 4 wherever there's an x inside our function. So we'll have the square root of 4, whatever that is, minus 2. So the square root of 4, we might know that as being positive 2, right? Because 2 times 2 is equal 4. So we'll have as a result 2 minus 2. And 2 minus 2 is going to be equal 0, right? Perfect. Okay, and so what we'll go ahead and do now is let's go ahead and try to plot these points on our graph. So let's see if I can get lucky here, and we'll go ahead and try to our every 2 tick marks will be equal to 1 unit. Let's try that. So I got negative 1 here on the left. I think that's the farthest x goes, but we can go ahead. If you wanted to, you can fill out more. It's always good to add more information if you're feeling like it's not enough. And then let's go ahead in the right direction. Well, that wasn't quite there on that point. And there's 1, 2, 3, and 4. 4 is the largest x value that we're plugging in. Okay, and so the outputs, it looks like they range from -2 to 0. So I want to make sure I'm recording the possibility for -1, -2, -3. And then let's just to even things out, I'll go ahead and add some values above as well. Okay, so I think I have enough. Your graph might look a little different than mine, of course. But let's go ahead and try to plot these points that we found. And I'm going ahead and change the color again. Okay, so our first point, when we plugged in -1, it gave us an undefined. So we'll go ahead and skip that one because our function is actually undefined at that point. The first point that we can plot, though, is when x is equal to 0. The output was equal, looks like -2, right? So when x is 0, the y value corresponding to that is -2. Okay, and now when we move on to +1, +1, when we plug it in for our x value, we, as a result, got -1 as the output, right? So that lives right there. Okay, and so the final point that we can plot is when we plugged in x equaling 4. If you remember the output or look at our table, the output was equals 0. So we're right here living on the x-axis. Okay, and so if you're familiar with square root functions, we know that they don't really look linear, or they don't look like a straight line, kind of like our absolute value had some straight line aspects to it. We know that this is going to be a little curved, and you can kind of tell if you visualize it before drawing that this curve is going to kind of follow a nice bend to it. Let's go ahead and I'm going to try to draw it for us. Connecting these dots, it's going to have this kind of nice curve to it. And on the left-hand side, we know, well, any x values that are negative, right? We would be taking the square root of a negative. And we can't do that, right? It's undefined. So we know that this is solidly the point on the left-hand side, or that I don't have an arrow on the left-hand side of the graph that I drew here. But however, we know that there are no issues if my x values grow off to infinity. I will have no issues in taking the square root. I mean, it might be something I'll use my calculator for, of course. However, we know it's possible. We're not going to break any rules. And so I can go ahead and add an arrow to this end. That will help us determine the domain and range. Okay, so this looks like it's a pretty good graph. And if I wanted, another thing you can do here is to label your graph. So I can say, well, this is g of x, and I don't think I did that above. So if I wanted to, again, right here. Okay, so if I wanted to, I could also label this guy up here as f of x. That's helpful sometimes. Okay, so moving back to part B, let's consider what the domain is. All right, so the domain here, right, we're thinking about all of the x values possible to plug into this. And so from our work that we did in plotting this, we noted that x values can't go beyond 0 as the lowest value of x, right? So the left endpoint of our domain is going to be equal 0, but we can plug that in to our function. We notice that on our table. We plug that in, and so we can use the square brackets on the left-hand side. And as we were discussing our graph, we were noting that all the x values, they can go off to positive infinity. As you know, as much as we would want, we could plug in larger and larger x values. And so we can go ahead and say the domain goes off to the right-hand side to positive infinity. And again, we use a rounded bracket in this scenario. Okay, so now moving on to the range, the last part of part B. We note the lowest y value as an output is indicated here at -2. It looks like when we plugged in 0, we, as an output, got -2. And that would be a square bracket to include -2. And just as the x values, they went off to positive infinity, we can see that the y values, even though it doesn't look like it's growing very fast, it will indeed continue off to positive infinity. Perfect. Okay, so moving on to part C. Okay, so same process. We're going to go ahead and start by plugging in these x values into our function. Wherever there's an x, we're going to go ahead and plug in these values indicated. So the first one is going to be 1 minus 2, the square root of this, right? Well, 1 minus 2, when we combine those, that's going to equal -1. And so in this scenario, right, we have something similar to what we had just seen in part B for the first value, and that it will have the square root of a negative value. And we'll go ahead and say this is undefined. Okay, so the next one we're going to go ahead and do, we're going to go ahead and plug in 2 as our x value. And so we have the square root of 2 minus 2, right? And so we'll combine 2 and minus 2, and that will be 0. And the square root of 0 is actually equal to 0, because 0 times 0 is equal to 0. All right, so moving on to x equaling 3, we have 3 minus 2 underneath the square root. And 3 minus 2 is equal 1. The square root of 1 is equal 1. All right, so finally, we're going to go ahead and plug in 6 wherever there's an x inside our function. 6 minus 2 is equal to 4, right? And we think about, okay, well, what is the square root of 4, or what number times itself equals 4? So we might say, that's 2. And we can confirm that on our calculator if we forget. Okay, so let's go ahead and see if we can plot this function. All right, I don't think I'll be able to use every other or two tick marks equaling 1 on this one because we have an x value of +6. So let's go ahead and we're just going to use every tick mark here is equal 1. So here's 1, 2, and actually maybe I'll go ahead and skip and do every other just so I don't get it too messed up looking here. So we have 3, and this would be 5, and this will be 7. I think that should be enough there for the x values. All right, and so now let's go ahead and think about the y values, the outputs. Go ahead and indicate this is 1, 3, kind of just following what I did in the x-axis, 5, right, and move in the opposite direction. I don't think actually I need to write any of these down here. I think we're okay. We didn't get any outputs of negative values, right? Okay, so let me go ahead and change my color and let's see if we can plot these points. So the first value, if you remember, we plugged in and we got the square root of a -1, which is undefined. So we'll go ahead and move on to x equaling 2. And let's go ahead and plug in 2. So when we plugged in 2, we had 2 minus 2, which is equal 0. And the square root of 0, we said that's equal 0. So when x is equal to 2, the output is 0. Okay, so moving on to when x is equal to 3, we plug in 3 into our function. We get 3 minus 2, which is equal 1. And the square root of 1, we said that's equal 1. Perfect. Okay, so now the final point here is when x is equal to 6, right? As a result, we see from our table, we got an output of +2. And so this will be our last point. Okay, and so kind of similar to what we actually had just done, right? We thought about the square root function and it has kind of a curve to it. And so I know that the x values can't go below 2, right? Otherwise, I would get a negative value. So I know that this will be my leftmost point, and I'm going to extend a line out from here and doing my best to try to draw a nice smooth curve. And we know, well, the x values, the only issue is if we plug in x values less than 2, otherwise everything's okay. We can just use our calculator, right, to find the square root of larger numbers, but the x values are completely okay to plug in. So let's go ahead and put an arrow here. I kind of follow the same pattern of writing, let's say this is h of x. That's a nice way of showing what this is. Okay, so let's see. What is the domain to this function, right? So we're thinking, what's the x values? What are the x values that we can plug into this function and everything will be fine? Kind of like we were just saying, right? The x values can't go below +2. Otherwise, we would have the square root of a negative value. But 2 is okay to plug in. We were able to plug in 2 and get the square root of 0 just fine. And the arrow helps us in our graph to indicate that as x gets larger and larger, everything's okay. So x, the domain, will go off to positive infinity. Okay, so moving on to the range, we're thinking about what is the lowest y value, that's an output of this function. And from our graph, we see that to be 0, right? And in fact, we are actually equal to 0 on the left-hand side for the range. And again, the arrow helps us from our graph to show us, right? The y values will go off to positive infinity. Perfect. Okay, so I think that was everything for this question. Let's go ahead and move on. Question 4. It looks like question 4 is giving us 3 different functions, and they're defined below And they're asking us in part A, B, and C, it looks like to evaluate values into each of these functions. So let's go ahead and start with part A of question 4. And they're asking us to find what f of -6 is. So what happens when I plug in -6 into the f function? So let's go ahead and copy down what the f function was, right? It's f of the f 5, that's a 5, 5 times the absolute value of -2 plus whatever our x value is, right? So let's go ahead and just plug in, that's -6. I'm gonna use parentheses here because I already have that addition symbol. Okay, so the first thing that I would like to do here is let's go ahead and kind of clean that up a little bit. Inside the absolute value, I have -2 plus a -6. And if I'm adding a negative value, that's the same thing as subtraction. So -2 minus 6 might look a little nicer to us visually. Okay, so if we have -2 and we take away 6, that means that we're going off to, looks like -8, right? If I'm thinking about that correctly. Okay, so -8, the absolute value of that is just equal to +8, right? So we can go ahead and get rid of the absolute value bars if we want. And I'm just going to use a multiplication dot symbol here to indicate multiplication between these two objects, 5 and 8. And you might remember this, 5 times 8 is equal 40. We can check it with our calculator if we prefer. But that would be the answer, right? That's what f of -6 is equal to for part A. Okay, so let's move on to part B. And they're asking us, well, let's find what g of 4 is. So now we're moving on to the g function, right? And we're going to go ahead and plug in 4 wherever there's an x inside the g function. So g of x starts out with 4 plus the square root of x minus 4. But here I'm plugging in 4 in the x position in this function. Okay, so let's start out by looking at that square root, right? Underneath the square root bracket, I have 4 minus 4. And 4 minus 4 is equal 0. And of course, we know the square root of 0 is just equal 0. So we'll have 4 plus 0 or just 4. So for part B, g of 4 is equal 4. Okay, so now finally moving on to part C, they're asking us to find h of -2. So we're moving on to the h function, h of -2. Again, we're just going to plug in the value -2 wherever there is an x in our function. All right, so h of x is a rational function. And in the numerator position, or the top of the fraction, it says 4 minus x squared. So here we want to be careful. I like to use parentheses. They're my friend here, right? Because when I plug in -2, I want to square -2. Okay, and that will be important here in just a second. So hold on to that idea. And the denominator on the bottom of the fraction, it's x plus 1. So I'll plug in the -2 where the x is and get -2 plus 1 in the denominator. Okay, so let's go back to this idea of the parentheses. Remember, the exponent of 2 indicates that we're just multiplying the object by itself once, right? Or -2 times -2. And so the parentheses help me because I know, well, if I had a negative times a negative, right? -2 times -2, the output will be positive. So let's go ahead and just write that result down without the exponent. -2 times -2 is going to be a +4. Perfect. Okay, so let's think about the denominator real fast, right? -2 plus 1, right? Looks like that's going to be equal to -1, right? Okay, so let's finish this off by looking back at the numerator of this fraction. And we see we have 4 minus 4. 4 minus 4 is equals 0, isn't it? And this is okay. We're not dividing by 0 in this scenario. We're actually just taking 0 and dividing it by -1, which is equal 0. Okay, so for part C, we found out that h of -2 is equal to 0. So that's every part of question 4. Let's move on to question 5. Okay, so it looks like we're going to take this g function, g of x, as it's shown below. And what we want to do for each one of the graphs below in part A through C is to go ahead and draw the transformations that are being described. Okay, cool. So part A is just saying, well, take g of x, whatever the output was of g of x, and just add 1 to the output, right? So this kind of transformation actually just shifts our function up 1 unit. So let me go ahead. I liked the red before. That helped it stand out, didn't it? Okay, so here, let's look at each of these dots, right? Um, Initially, when x was -3 into the g function, the output was 0, right? I'm looking at that leftmost point, -3 comma 0. Well, if I add 1 to 0, the result would be +1, right? So it's still the same x value, it's -3, but the output, instead of being 0, we're adding 1 to that. So it's going to be equal to 1. Okay, let's move on to the next point. It looks like that next point is at x equaling -1, and the output is -2. And so what I want to think about again is when I take -2, I will add 1, which I think will result in -1, right? And so the x value remains the same. It's still -1, but the output is -1 now instead. So we kind of see this pattern arise, right? We can kind of, through similar reasoning, see the output when we plug in x equaling 1 is -2. And so the output here, right, the new output will be adding 1 to -2, and so we'll get -1 again. And very similar to where we began, right? The output was 0 when we plugged in 3. And so when we add 1 to that, we'll end up here. Okay, and so let's do our best. We'll connect these dots, right? And you may have come to this in a different way, right? Just thinking about, well, if I'm adding 1, I'm just shifting everything up 1. But this was a nice way to break it down point by point. Perfect. Okay, so moving on to part B, right? Part B is a little bit different, right? We're subtracting 2 on the inside of the parentheses, right? So whatever the initial x value was, we're going to go ahead and take away 2 from that. You might remember from studying transformations, right, that it's going to have a horizontal shift rather than the vertical shift we saw in part A. Part B is describing a horizontal shift because it's happening on the inside of the parentheses. And these happen in the opposite way that we would assume, right? If this were g of x -2 on the outside of the parentheses, we might think, oh, this would just go down 2. And so you might think, well, this will just go left 2. However, what will happen here is this will move to the right 2. So here is this point here, right? We're moving this one to the right 2. And let's go ahead and I'll try that same method. I'm taking this point and I'm moving it right 2 units. So it's going to end up here, right? And so I know this is kind of confusing the way that I've been drawing it, but I'm taking this original point here and moving it to the right 2 units. So it's going to end up there. And then finally, this point here, moving it to the right 2 units, it's going to end up over here. Okay, so let's go ahead and try to clear things up by connecting these dots, right? Perfect. Did my best here to draw some straight lines. All right, so we see kind of as we theorized, right? Everything is just going to be moving to the right 2 units. And that's our horizontal shift indicated in part B. Okay, so moving on to part C, we see that we have -2 times the function g of x, right? So here, if we were just looking at, say, the negative first, we know that if it was negative g of x, what that would do is basically flip this across the x-axis, right, or the horizontal axis. So that's helpful, right? Because that helps us kind of gauge where we're going with this, right? So looking at the first point when x is -3, if this were flipped across the x-axis, it's actually going to start just by landing here, right? Because it's flipped across the x-axis and it's on the x-axis, so it's just there. And then we're going to be multiplying it by 2 as well. Well, the output here is 0, and 2 times 0 is equals 0. So this point, actually through this transformation, is actually just staying right here. Okay, so moving on to the next point, when x is equal to -1, the output originally was -2. So first, we think maybe about the negative aspect, and it's flipping it across the horizontal axis. And so initially, we would think, okay, it's showing up here, right? But the output then is 2, and we're multiplying by 2. And so 2 times 2 is equal 4. So we're actually up here. Okay, and actually it's a similar process for the next 2 points, right? It's the same story, right? Initially, we might think about the negative being multiplied by g of x. That flips everything across the horizontal axis, right? We're at +2, and then 2 times 2, again, is equal 4. And then finally, when our output was 0, not much happens, right? We're still hanging out here at x equaling 3, y equaling 0. Let's go ahead and connect these dots, right? Just like this. And you might have theorized or come up to this in a different way, but we see that this -2 both flipped the graph and vertically stretched it. Okay, so let's move on to question 6. Okay, so question 6 asks us to graph the piecewise function by plotting points. Okay, let me go ahead and switch my color of my ink here. So this kind of feels familiar, right, to I think a question that we had above. And so what I think we should do here, right, is possibly come up with a table of values, right? Let's go ahead and do that. That might seem familiar to you. This might help us graph this function. So I'm going to say, well, the inputs are going to be x values, and the output is going to be whatever f of x is when I plug in that x value. Okay, so the piecewise function here, it looks like it changes, the function changes, right, between x is less than 1 and x is greater than or equal to 1. And I'm looking here at this right here to see that. So the x values, because I have to choose those x values, right? They're not giving me a table that's halfway filled out. So I want to take maybe some values less than 1. and maybe some values equal to 1 and greater than 1 as well. So let's go ahead and I'm going to go ahead and pick -1 because that's less than 1. 0 is less than 1. And then maybe let's pick some values that are equal or greater than 1. So I'll just choose 1, right? That's equal to 1. And then let's go ahead and do +2 as well. Okay, so your numbers might be a little different, but the point being is that it might be helpful for you to create a table of values for this. And so let's go ahead and evaluate the ones that I chose. X equaling -1, when I plug this into the function, right? This is a piecewise function, and so we'll look at it thinking, well, the X value of choice is -1, and that's less than 1, right? So I'm going to go ahead and use this function, -3x, when I have x equaling -1. So I'll have -3, right? -3x, and I'm plugging in x equaling -1. So I have -3 times -1. And -3 times -1 is going to be a +3. Perfect. Okay, so still on that same trend, I'm going to go ahead and look at the next x value of 0, which is, of course, less than 1. So I'm still using the same -3x function. And here, instead of x, I'm plugging in 0. We know that -3 times 0 is going to be equal 0. Perfect. Okay, so moving on now to x equaling 1, right? So we see, okay, well, x equaling 1, that's greater than or equal to 1. So the function we're going to use is -3. So this might feel a little weird, right? Because there's no x for me to plug in +1. In fact, when x is equal to 1, we just say its output is -3, as it's stated, right? And this will be cemented a little bit more possibly, right? When we think about x equaling 2. 2 is greater than or equal to 1. And the function, no matter what the x value is just equal -3. Okay, so we've created a table of values. Again, you may have gone a different route, but I find it helpful to draw up this table of values for myself at least. And so I'm going to go ahead and plot these points. All right, so let me go ahead and label some things here, X and Y. And I'm going to go ahead and use every 2 marks as equal 1. I need to go beyond -2, of course. Go off into the right direction, 1 and 2. And then let's go ahead and mark down some Y values, both in the positive and negative direction. I think I need at least up to 3 and down to -3, actually. So -1, excuse me, -3. Okay, so I've got it set up. I'm going to go ahead and try to plot this. And let's see here. All right, let's plot the first point. The first point was at -1. And the output from our table of values is equal to +3. So when I plug in -1, the output is +3. Okay, and so moving on in our table of values, the next point here is x equaling 0, and the y value is equal 0. All right. So this actually is the first function in our piecewise function. So we could, if you wanted to, we could draw a line here to indicate, at least between these 2 points. And in fact, this can go off in the left direction, right? As far as we want to go, right? As many x values as we want, right? We know that this is an indicator of what that function looks like. Okay, and so what we might conclude at this point, for the red line that I've drawn so far on our graph, we note that this follows this pattern, negative 3x. This looks like a linear function. We might be accustomed to hearing that. All the way up till we just before x equaling 1. So I can actually extend this line beyond the point I've drawn here. And it's going to follow a similar pattern. Let's see, it's going to go ahead and let's see. If x were equal 1, I would have negative 3 times 1, and the output would be negative 3. And so I know I'm kind of going off in that direction. We had a straight edge, it would be a lot easier. But I know it's not actually equal here, right? So it's going to be an open circle for now. Okay, and so now let's go ahead and move on to plotting the next 2 points. The next 2 points is x equaling 1, and the output is negative 3. So actually this point here, it's kind of large open circle, but I can go ahead and plug that in, right? We saw that in our table of values that I drawn up. And the next value that I have here is positive 2, and the output was again negative 3. And in fact, this is what we were observing before. As we go off beyond x equaling 1, it's just going to be a flat line, always equal negative 3. Perfect. Okay, so this would be, I believe, everything for question 6. Let's go ahead and move on to question 7, in which we're working with a piecewise function again. And we're asked to evaluate the function for the given values of x. Okay, and so here in part A, they're asking, well, what is, let me change my color back, right? What is f of negative 3? So part A is f of negative 3. So similar to what we have done before, right? We want to plug in negative 3 wherever there's an x, but we have to first indicate which function are we using, because there's 3 different functions described in f of x. And we want to see, well, x is less than, or sorry, x is equal to negative 3. So we look on the right-hand side at all of this information. And we see, well, negative 3 is less than negative 1. So I'm going to be using this function here first, right? Okay. So it's negative x minus 1. So I'm going to plug in my negative 3 wherever there's that x. And again, I'm using parentheses. Parentheses are my friend here. And so we have negative 3 minus 1. So our first step might be to get rid of that double negative, right? If I had a negative 3, that's positive 3, isn't it? So we'll have just positive 3 minus 1. And 3 minus 1, that's equal 2. Okay, so here we see that f of negative 3 is just equal to. So perfect, that's everything for part A. Moving on to part B, they're asking what is f of negative 1? So again, we start by looking at the right side of our piecewise function, and we see where this x value lives. And note that x actually equaling negative 1 lives between negative 1 and 2. And so, or x negative 1 less than or equal x less than 2. So we'll go ahead and use this function, right? And if there is any x's in our function, we would plug in negative 1. In this scenario, it actually is just equal negative 3. So f of negative 1 is equal negative 3. And that's everything for part B. Part C, they're asking us to find what f of 2 is. And so we start by looking at the right-hand side of our piecewise function to see where this x value of equaling 2 lives. And it is the last function, right? 2 is greater than or equal to 2. And so we're going to use this square root function described. So we have the square root and our x value is equal to, so we'll plug in that 2 where the x is. And so we'll have the square root of 2 minus 2, which 2 minus 2 is equal 0. And the square root of 0 is equal 0. Okay, so the last one for question 7 is part D here, and D is saying, what is f of 6? So 6 is greater than or equal to 2. So looking at the right-hand side of our piecewise function, we see, okay, if x is greater than or equal to 2, we use this square root function. So I'm going to go ahead and draw my square root and plug in 6 where the x was. So x minus 2 now is 6 minus 2. 6 minus 2, that's equal to 4, right? And so we have the square root of 4. And so the square root of 4, that's going to be equal to. Perfect. Okay, so that was everything for question 7. We'll move on now to question 8. Question 8 is a story problem talking about a cell phone plan with some additional charges. And they give us this monthly cost function. And in terms of x minutes, C of x is the monthly cost. And it might look similar to what we saw in question 7, in that it's a piecewise function. So we'll be using this information to answer parts A, B, and yeah, let's go ahead and get into this. Part A is asking us, how much would it cost if you used your phone for 250 minutes 1 month? Okay, so here, if we recall from the description of this problem, x is equal to the number of minutes used per month. So when they say 250 minutes in 1 month, we see, they're asking us, right? When x is equal to 250, what is the output? So they're asking us, well, what is C of 250? So we're using, a piecewise function for C of x. So we have to look on the right-hand side and think about, where does 250 live in these intervals? And note that 250 is between 0 and 600. Thus, the output will be equal to this guy here, right? And it's actually just equal to 63.97, right? There was no x value associated with that. The output was just 63.97. And so since this is a story problem, we kind of want to put it in context of this exact scenario. So we'd probably say something like, it would cost, right? Because they're asking how much it would cost if we use 250 minutes. It would cost, right? The output of this function is in dollars. So it would cost $63.97. Perfect. Okay. So moving on to part B, they ask, how many minutes would you have used in a month if your bill was $235.97? Let me get the problem statement a little bit in here as well. So here they're saying, well, what happens if the cost was $235.97? So if you remember, this C of X function was the cost function, the monthly cost function, and that the output would be equal to the cost. So I can go ahead and say for part B, I think what they're asking us here is what are the X values? How many minutes, right? How many minutes would you use if the bill is 235.97? Okay, so what we want to do is kind of reverse engineer this, right? So let's see, we know that if the minutes were between 0 and 600, it would just be a flat cost of 63.97, right? And I'm getting that information up here. So since 235.97 is definitely not 63.97, I think I can then conclude that this would be the function, right? We're well over, I believe, 600 minutes in this scenario. So let's go ahead and take that function, right? Because this is what C of X will be equal to. C of X will be equal to 63.97 plus 0.4 times some X value. I don't know what that is yet, minus 600. And so this was what my C of X is equal to, right? But I also just stated that C of X will be equal to $235.97. Okay, so now we're being tasked to solve for this X value, right? So let's attempt to kind of manipulate this to isolate our X, put it on one side, get everything else on the other. First, I would probably subtract 63.97 from both sides of this equation. So minus 63.97. I want to do the same thing on the right-hand side. And I think the result here is going to be 172, if I remember right, on the right-hand side, that is. Of course, on the left-hand side, if I took 63.97, subtract 63.97, I just get 0. So as a result of that first step, we have this. Okay, and so next I'm going to, I think either you want to think about it, I think as dividing by 0.4 on both sides, right? Let's go ahead and divide off the 0.4. As a result, on the left-hand side, we're just left with X minus 600. And on the right-hand side, we're going to be equal to 430. And so now we just have X minus 600 is equal to 430. So I want to go ahead and add 600 to both hand sides. And we'll be left, let me go ahead and move my results up here, right? X will be equal, yes, we're well over that 600 in minutes, right? X is equal to 1,030 minutes. And so you might answer this when they asked how many minutes would you have used in a month if your bill was this amount? So we would probably answer it with a sentence and saying, I would have used, right? Remembering that the X value is the number of minutes. So I would have used 1,030 minutes. Perfect. Okay, I believe that's everything for question 8. Moving on to question 9. They're asking us to determine if the function is odd, even, or neither, and that actually we're supposed to use the definition of odd and even to support the answer. Okay, so here, what we could do, right? One method of finding these results would actually just be to plug in For example, in part A, I might plug in a negative x, right? And see what the results are, right? As I plug in this negative x, right? I see, well, what I'm saying here is that anywhere there is a positive x, or just an x in general, I should say, I'm going to put in a negative x instead. So f is equal to 1 over x. So I'm going to go ahead and plug in the negative x instead. And so I get 1 over negative x. And if I wanted to, I could actually go ahead and pull out the negative out front, right? That still indicates the same function. And here, observe that we have -1 times 1 over x. So 1 over x, as indicated in part A, is actually equal to the function f of x, right? So I can go ahead, instead of writing 1 over x, I might write f of x, but I have to indicate the negative sign on the outside, right? So here we observed that f of negative x, right, is equal to negative f of x. So this implies that the function f of x is odd, right? This is the definition of an odd function. Okay, so we're going to go ahead and repeat the same process for parts B and C. So I'm going to go ahead and part B, plug in a g of negative x, like so. And so everywhere there is an x, I'm going to go ahead and just plug in negative x, just at first. That's supposed to be a 3 minus 2 negative x. Let's go ahead and make that 3 a little nicer. Okay, so what happens if you take a negative x and you cube it? That is, you multiply it by itself 3 times, right? Well, another way you might think about this, let's think about this, right? So we could also possibly split this up to -1 cubed, right? -1 cubed times x cubed, right? I'm just kind of splitting this up, applying the exponent to both the -1 coefficient of x and the x itself. And then next, I might take this negative and distribute it out, right? And pull it out. And so that would be, what would that be? -2 times -1. That's equal to +2x. Okay, so let's go ahead and clean this up because it looks like I've just made things worse. -3 cubed, what is that equal, right? -1 times -1 is equal +1. And then if I were to multiply that by -1 once more, that's equal to -1. So I'm going to go ahead and pull that -1 out front and just indicate it as a negative sign. So I'll have -4x cubed plus 2x. All right, that's looking a little cleaner. In this trick here is another one we can do, right? We can go ahead and factor out a -1 out front. And so if I pull a -1 out of -4x cubed, I'm actually just left with 4x cubed. And if I pull a -1 out of +2x, I have to change the sign, right? And feel free if you need to multiply that -1 back in to see this. That's a good way of doing it. So 4x cubed minus 2x. This should look familiar. This is actually just our g function, right? So I can actually just write g of x. But I need to remember that a negative needs to be out front. So what we have observed is that when you plug in a negative x into our function, that negative comes outside of the function. And again, This is an indicator, right? This is the definition of an odd function. Perfect. Okay, so moving on to question C, or part C. We're going to do the same thing. We're going to go ahead and ask ourselves, what is h of negative x, right? So wherever there originally was an x in this h function, I'm plugging in a negative x. So here it's 5 times the square of negative x. And if we were to take this and we could actually break it apart the way that I just did, but you might already know, but I'll go ahead and walk us through this, right? I could pull out the -1 coefficient and square that and multiply that by x squared. And so here it looks like I've messed things up, made it worse, but we can say, well, what is -1 squared? That, of course, is -1 times -1, which is equal to +1. And so we're left as a result just to be equal to 5 times x squared, which, if you remember, this is actually just equal to our function, right? So if you plug in a negative x into our function, as a result, you just get the original function out. And this is the definition of an even function. Perfect. Okay, so that's everything for question 9. Moving on to question 10. It says, given a function f and a function g, find the following. And it looks like we're going to be doing a different kind of composites of functions here. Okay, so in part A, it's nice. Actually, they're just asking, well, what is f of 4? And so we've done this kind of thing already in this review. We're just going to plug in 4 wherever there's an x in the f function. Okay, so you might use a calculator if you don't already know what 4 times 4 is. That's equal 16, right? So we have -2 times 16 minus 3. -2 times 16, that looks like that's going to be equal to -32. And -32 minus 3, I believe, is -35. Perfect. Okay, so let's move on to part B. Part B, it's got some interesting notation, doesn't it? It's got this f minus g of a, is how I might read that. I'm going to go ahead and just right away do some rewriting of this, right? Because what this is indicating to me is that I'm going to plug in a into my function f and then subtract the results when I plug in a into my g function. So this might be a way of rewriting it, kind of clear some things up, right? So now we're just going to start by plugging in a into the f function. So wherever there was an x, I'm plugging in a. So -2a squared minus 3. That's what f of a is equal to. And so now I'm going to subtract what happens when I plug in a into the g function. So here, I find it best to use parentheses, right? Because I have this negative out in front of the g of a function. For reasons we'll see here shortly, it's important to write these parentheses to make sure that those signs line up. But I just want to plug in a into the g function. So it's going to be -2a plus 4. Okay, so now I have this all written out. In this step, I can go ahead and distribute, right? I want to simplify and combine like terms if possible, but I think I want to go ahead and distribute this negative into the parentheses, both to the -2a and the +4. As a result, I get -2a squared minus 3. That's my first part of this. And then I have a -1 times a -2a. That, of course, is equal to +2a. And a -1 times a +4 is equal to -4. So here, in order for me to clean the remainder of this up, I actually only have two like terms, -3 and -4. And so let's go ahead and combine those. I have the -2a squared. And I'm going to go ahead and bring the 2a up front, and then -3 minus 4, that looks like it's just going to equal -7. Okay, so that's everything for part B. On to part C. This one, it looks like is indeed a composite, right? F of G of 3, right? So what we want to do is look on the inside of this first. What they're asking of us is to take whatever the result when we plug in 3 into the G function is, and we're going to take that result and plug it into our F function. So I think what I would probably do is stickler for this. I would probably just continue to write the F on the outside. And now what I want to write on the inside, though, is this new updated G of 3. That is, I can go ahead and write the definition of the G function with the evaluation of 3 wherever there is an X, right? And then close the parenthesis at the end. Okay, so I should now have this kind of worse looking thing, F of -2 times 3 plus 4. But I can go ahead and simplify the stuff on the inside of this F function before I evaluate it. So I would have -2 times 3. That's going to be equal to -6. -6 plus 4 is going to be equal to -2. So we have, instead, we're just evaluating -2 into the F function. Now we can turn our attention to the definition of the F function, right? It was equal to -2 times x squared, which here is -2. Here, it's important, again, to use parentheses, right? Because we want to take the square of -2 and not just 2, and then subtract 3 on the outside like that. Okay, so -2 times -2, right, is equal to +4. Right, so let's go ahead and write that down so we don't get messed up here. There's a lot of -2's. And then next we see, well, -2 times 4 is equal to -8. And then -8 minus 3 is equal -11. Perfect. Okay, so that was everything for part C. Let's move on to the last part D. Part D, it's got this interesting notation here. It's not a multiplication symbol with a dot. It's this open circle, right? So if you're familiar with this, this is, again, the same or similar to what we had seen in part C, in that it's a composite, right? I might write this instead, if I wanted to, as G of F of A. I find it kind of helpful sometimes to rewrite it to the form that we're comfortable with, and then we can work through it. So here I'm going to go ahead and plug in A into the F function to start, right? So plugging in A into the definition of F, I get -2 times A squared minus 3, just like so, and close the parenthesis. And so now I'm going to take that big expression and plug it into the G function as defined, right? So G is equal to -2x plus 4. So everywhere there's an x, I'm going to plug in this -2a squared minus 3, and then add 4 on the outside. Okay, and so here, in order for me to kind of clean things up, I'm going to start by distributing this -2 inside the parentheses to both this -2a squared as well as the -3. So -2 times -2a squared is equal 4a squared, positive 4a squared. And -2 times -3 is equal +6. And then we have the +4 hanging out there waiting for us. Okay, and so now I just want to combine like terms if there are any. And so notice that there actually is just the two, right? 6 and 4. Those are the only like terms here. So we have 4a squared plus 6 plus 4, or just plus 10. Perfect. Okay, so that's everything for question 10. Moving on to question 11. They give us, looks like some graphs of three functions, and they're asking us to determine whether each of the functions is one-to-one. And we're then also asked to justify our answer. And so if you're familiar with this test, we would use the horizontal line test. That is horizontal, not the vertical line test. And so what we want to do is to attempt to draw some horizontal lines on each of these functions. So for example, for graph 1, right, I might just throw a horizontal line and see how many times does this intersect with the function described in graph 1. And we see it happens twice. And so this is an indicator that it fails the horizontal line test because it crosses more than once. And therefore, what we can conclude from that is that graph 1, right? So graph 1 is therefore not one-to-one, right? Because it doesn't pass the horizontal line test. Okay, so moving on to graph 2, we would then use the horizontal line test again. So horizontal line test may not prove to be beneficial in this scenario, but it will if you draw that horizontal line right here, right? So notice that this intersects 2 points. And so therefore it fails the horizontal line test, right? Graph 2 is not, it doesn't indicate a function that is one-to-one, or it's not one-to-one, right? Okay, so the final graph, right? Graph 3, we could choose a horizontal line. I think pretty much anywhere will show that it fails the horizontal line test. I'm gonna go ahead and draw mine maybe down here and see, this this intersects way more than once, right? 4 times. And so then we conclude it fails this horizontal line test, right? Graph 3 is not one-to-one. And so a good justification of your answer might be this one-to-one test, right? If you have other reasonings, you obviously can go ahead and describe it that way, but that would be question 11. Question 12, they are asking us to use the composition of functions to determine if the functions are inverses of each other. Okay, so yeah, this is really cool. What we should, as a result, right, when we do these compositions, say, for example, I did f of g of x, if f and g are inverses of each other, as a result, this should be equal to x, right? And the opposite would be true as well. So I should be able to plug in f into g, and this would be equal to x, right? And this is kind of a visualization of the undoing of the function that the inverse does. So this is the goal, right? Let's go ahead and see what happens. For part A, let's go ahead and take the f function and plug in g and see what the result is. Okay, so the g function is negative x minus 2. Let me go ahead and just write this step, negative x plus 2. I don't know if I said plus or minus there, but f of negative x plus 2 is what we were going for. And so I'm going to go ahead and take this expression, negative x plus 2, and plug it into the f function wherever there's an x value. So here the x value is out front. I get negative x plus 2. That's the expression I plugged in. And then I get minus 2. Okay, so here the twos cancel, right? I can combine those. They're like terms. 2 minus 2 is just equal to 0. So I'll be left with negative x. And, this might feel like we're on the right path, right? Because we got an x, right? But notice that it's a negative x. And so here, this negative x obviously is not equal to positive x. And therefore, this doesn't pass the first qualifier, right? For this to be an inverse or these to be inverse of each other. So we actually could stop here, right? And just say, well, this is, not inverses. Okay. So now we can move on to part B. Part B is giving us new functions, f and g. And we're going to go ahead and just verify, right? F of g of x, see what this is equal to. So g is equal to 2x plus 3. And if I plug that expression into the f function, wherever there's an x, I get 2x plus 3 minus 3 in the top of this fraction, and then divided by 2 in the bottom. Okay, and so here we combine like terms, right? We get the 3 minus 3, that's equal to 0. And we get 2x over 2. And what we could do here is cancel out those 2's, right? 2 divided by 2, that's just equal to 1. And I don't have to write that 1 if I don't want to. This is just equal to x, isn't it? So perfect. This is exactly what we wanted, right? We've shown that at least it's kind of fulfilling the first quality, right? For these to be inverses of each other. So let's go ahead and check in the other direction as well. Let's say, well, what is g of f of x, right? So we're going to go ahead and take the f function, which is x minus 3 divided by 2, and plug it into our g function wherever there was an x, right? So g was 2x plus 3. We're going to go ahead and plug this expression x minus 3 over 2 into this. And so right away, depending on what you need to observe this cancellation, we see that this 2 can be written as 2 over 1 if we wanted. And if we were multiplying a fraction times a fraction, we're actually just kind of squeezing the top of the fraction together and the bottom of the fraction. And so what you'll kind of in a roundabout way see, right, is that, let's go ahead and just write this step. 2x minus 3, that's me squeezing together the top of the fraction, right? With multiplication of fractions, it's nice like that. The bottom becomes just 2, right? Because 1 times 2 is equal to, right? And so here we'll see those 2's cancel, don't they? 2 divided by 2 is just equal 1. I don't have to write that 1 if I don't want to. So I just get x minus 3 as a result. And then don't forget to add the 3 on the outside. Combining the last like terms, right? Those 3's is just equal to 0. So we would have x plus 0 or just x. So perfect. What we've just found, right, is that the first quality holds, that when we plug in g into f, we get just x back. And if I plug in f into g, I just get x back. So this is an indicator that this is indeed, they're inverses of each other, right? Perfect. Okay. Moving on to question 13 is another story problem. And so we're dealing with data, looks like some blood pressure data from some people, some healthy adults. And so this P of X is the blood pressure, and X is, blood pressure, and it's measured in the units of mmHg, and the age X is measured in years. Okay. So in question or part A, they're asking us to find what P of 21 is. Okay. And so what we're maybe being tasked to do here initially is just to look at when X is 21. What's the output, right? So P of 21, what's the output? So we'll go to X, remember, is the age measured in years. So we're going to go ahead to go to 21 on our table for the age, right? And just look to see what the output is, right? The output is 118. Okay, so this is just the first task, right? Now they're asking us to write a sentence, including the units, explaining what it means in the context of the situation. And so for this scenario, this would be the blood pressure of, it looks like the blood pressure, right, of a 21-year-old in MMHG. So you might write something like the blood pressure of a 21-year-old is 118 mmHg. And of course, this is the 21-year-olds that were a part of this survey. Okay, so question or part B here. They say, well, find, and they have this notation of p to the -1. This would be read as find the p inverse of 134 and write a sentence explaining what it means in the context. Okay. So in this scenario, right, we're asking ourselves when the output is 134, right, because the inverse, right, is dealing with the outputs of the original function and putting it as the inputs in the inverse function. Sorry if that wasn't clear. What part B is asking us is what would be the input in the original function that indicates 134 as the output from the original function. So what we would do is look at the outputs, right? The blood pressure information on this table when it's 134. And so that's here, right? And so we're asking ourselves, well, what's the original input? And that is 64. So here I could just start by saying, well, P inverse of 134 is equal to 64. All right, and so this is only part of the answer, right? Now we're asking ourselves, what does this mean in context of this problem? So you might say something like, okay, a blood pressure of 134 mmHg. So a blood pressure of 134 mmHg, right? Not forgetting those units. Maybe is correlated or something of that effect. Correlated to a 64-year-old, right? So that was our output there. Perfect. Okay, so that might be one potential answer to that. Okay, so for part C, they want us to find the average rate of change on the interval 38 to 58, and then to connect it to the context of the situation by including a sentence. Okay, and so here, let's think about this. What we want to do is find the average rate of change. And so you might have an idea of this or a definition somewhere, right? So average rate of change, right? This equation, I think, no matter what, should look familiar, right? Let's think about this. This is going to be whatever the blood pressure is of the left or the right endpoint minus the left endpoint. And then, of course, just making sure to line these values up. So this is the average rate of change on A comma B, right? And so here our B value is equal 58, right? So we're going to do P of 58, that's our B, minus P of our A value, which is 38, right? I'm getting that information from this guy up here. And go ahead and fill these in down below as well on the bottom of this fraction. Okay, so I need to go back up to the table to see what the blood pressure is of a 58-year-old. And I see that here, right? Blood pressure of a 58-year-old is 132 mmHgs. Let's go ahead and put that in. 132. And the blood pressure of a 38-year-old, right? That's here. It's 124 mmHg. So minus 124. And then the bottom, 58 minus 38, that's equal 20. Okay, so the top of this fraction, 132 minus 124, that's going to be equal 8, right? So we'll have 8, and then the bottom again is just 20. And this is equal, if we simplify this, is equal to 2/5 or 0.4 if you put that into your calculator, or you might know that already. So this would be just the first part of this question. We found the average rate of change on the interval 38 to 58. So we have to put it into context in a sentence. So what your sentence might look like, here's one potential. The average rate of change of blood pressure. Maybe I'll just say BP for sake of time. Um, increases the average rate of change of blood pressure increase per year is 0.4. But what are the units of this, right? So initially I had said that the results in the top were millimeters times Hg, or millimeters Hg. And the bottom, I didn't say it, but it was years, right? So mmHg per year. That would be the units spelled out. And this would possibly, you could add something like for participants from 38 to 58 or something like that. But this would be a good start. Okay, so moving on to question 14. Okay, and it's another story problem to finish things off. Um, and so they give us this, looks like based on data from a hurricane, the relationship between the barometric pressure, B of W, measured in millibars, and the wind speed, W, measured, it looks like in miles per hour, is given by this function, B of W, described. And so in part A, they're asking us to find the barometric pressure when the wind speed is 100 miles per hour. And then we're to take that result and round to the nearest millibar, okay? Okay, so they are giving us a wind speed, and that wind speed is in the correct units, right? That wind speed's in 100 miles per hour. So what they're asking of us is, what is B of 100? So what we'll do is plug in 100 wherever there is a W in our original function and simplify to find the results, right? So 1,220 minus 100 is 1,120 divided by 1.17. And so let's see, that's the result. Rounded to the nearest millibar is 957. And so you might, since this is a story problem, you might give your answer in a sentence. So the result here is a result of barometric pressure when the wind speed is 100 miles per hour. So the barometric pressure, just shorten it to BP, when the wind speed is 100 mph, is 957 millibars. Oops, there we go. Okay, so moving on to part B. And they ask us to show all of the algebraic steps involved in finding the inverse function, B inverse of x, where x is the output of B. Okay, so we might start by just observing what was told, that B of W is equal to 1,220 minus W over 1.17. So the first step in finding an inverse, for myself at least, this is how I like to do it, is to go ahead and just rewrite this. Instead of with the B of W and W, I'm just going to simplify things by writing Y and X instead. The output is typically your Y value, and the input is typically your X value. So go ahead and just make that substitution if you'd like to begin. The next step here, right, in this process that I like to do is to go ahead and just basically flip these, right? Switch the X and the Y. So I'm going to go ahead and instead of writing Y on the outside, I'm writing an X. And then instead of the X on the inside, I'm going to write the Y. Perfect. Okay, and so next we're going to go ahead and attempt to solve for our new Y here, right? Okay, so our new Y is hanging out inside this fraction. And the first thing that we'll probably want to do, right, is to multiply both sides of this equation by 1.17. So we'll get 1.17x, and this will be equal to the 1.17 in the denominator will go away since we multiply by 1.17. And I think we're not too far off here from getting what y is equal to. I'll probably move down here though. Excuse me. So here, and depending on how you like to look at this, the result is going to be y is equal, and I think I'm going to have to subtract some things and add some others. So I think what I'll get here is y is equal to, I'm going to go ahead and write this 1220 first, minus 1.17x. Okay, so yeah, I'm jumping a few steps here, but you should be able to get to this point here. Okay, so now we've solved for this new y. And at this step, what I find to be best here is to now, instead of writing y, this is now my inverse function that I've found. So b inverse of x is equal, and I actually already have my x already lined up in this. So we're all set. So this would be the new inverse function. Perfect. All right. So I think I've answered everything. Show all algebraic steps involved in finding the inverse function b of x, where x is the output of b. Perfect. Okay. So moving on to part C. Looks like they want us to use the equation that we found in part B to evaluate 50 into it. And then, of course, explained what this is in terms of this context. So B inverse of 50, we're just going to ahead and plug in 50 wherever there is an X in our inverse function. So we should have this. Okay, and so I don't have a calculator close by. I'm going to go ahead and just use the results I had found before, right? So I have 1,220 minus 58.5. That's 1.17 times 50. Okay, and so if I combine these, you should be getting 1,161.5. Okay, and so here next, right, this is only the first part of this question. Now we want to um, explain the meaning and context in using units as well. So one potential answer might be when the barometric pressure is 50 millibars, the wind speed, right, is what we just got, right? That 1,161.5 miles per hour. Perfect. Okay, so that I believe was everything in terms of the questions for the test one review. If you have any further questions, of course, feel free to reach out to your instructors or anyone at the math desk or in the tutoring center for more help. I hope you have a good day. Thank you.